always a factor. All right. So for homework, just do page 17. It's not a lot. It's pretty much what we were doing. Yeah, it was for you to kind of put together the things that we covered in class yesterday. So
We already did that.
when we're talking about designing a confidence interval, the two things we want to have in mind is we want to simultaneously have a high confidence but also a narrow confidence interval. Right? So those are the two big challenges. So you kind of want to have your cake and eat it too. And so hopefully this example kind of gets that idea across. So it's still the same idea with the Westchester homes. We have a simple random sample of 40 with a mean price of 730,000, standard deviation about 60,000. We found in the last example, a confidence interval was those values rounded. So we had to do a 90% confidence interval and also a 99% confidence interval. Yeah. So just crank that out real quick. Stat test option, it's a T interval. I'm sorry, Z interval. We're not at T yet. Still under stats. 730,000 was the mean with the n value of 40. And the confidence level will be 0.9. So we get this interval, which is, it's an interval. So I'm just going to indicate the values, 714,395-ish. .54, I'll put it in the decimals, 548, comma, 745,604. 0.452. All right, doing the same thing with a 90%, 99% confidence interval estimate. Right. So stat, let me quit out of there first. Stat test Z interval, this time 99% confidence. And we get these values, 705, 563, 0.538, 754, 436, 0.462. All right, so what do we notice about this as it compares to, or both of these, as it compares to the 95% confidence interval estimate?
The 90% interval is narrower than 95%, whereas the 99% is wider.
Narrower versus wider. All right. So then the big question, and this is where we kind of sum it all up, and we kind of derive the whole meaning from all of this. Let's say a real estate agent comes to you and asks, how confident are you based on your data that recent home sales in Westchester are somewhere between 720,000 and 740,000? You know, what are you going to say there?
I'm uncertain because based on the intervals that I took, all of them encompass that range, but they also have numbers that are outside that range, either lower or higher.
Right, so we would say uncertain. Let me just get my pen to work consistently. Because so you said all of them encompass but have values outside of it? Yeah, what did you say again?
Oh, uncertain because the interval read included this range, but also had several numbers that were either above or below that
included, but had several numbers beyond that range. I'll write values. All right, that's a reasonable answer. Now, how confident, that could call for a qualitative or a quantitative response. So if you had to get pinned down and give a number here, what would that number be?
It will probably be around 92 to 93%.
92 to 93%?
Because it's certainly.
So we're saying 92, let me write that down, 92 to 93. So, you know, like, let me say, I'll be a little bit more vague. So between 90 and 95%. Right. So we have the 90% confidence interval here and the 95% confidence interval there. Now, both of them encompass what we're looking for, right? They both seem to have that 720 to 740 in it, but as we increase from 90 to 95, we're widening our interval. So we're getting less and less, well, I'll say certain, right? So, you know, it's that whole idea with the age analogy that I gave yesterday.
90 to 95 doesn't work.
Would it be less than?
Yeah, it has to be less than 90.
Well, we're just assuming that we're working with these reasonable.
Well, then none of them would work because you have 711,000 and then you go wider, but no narrower, but
Well,
it's only 714.
Nothing's ever gonna work.
I know, but like,
So, it's just what's the best of the bad situation here,
well, that's
right? Because Evan gave us uncertain, so I want a number.
Yeah, but you can't pick between those numbers
Can we
because
pick outside
between
of
those
these
it
numbers?
doesn't
Like, I was
encompass.
85% sure.
You could, but then I mean, if you tell somebody that you're 85% sure of something, it's like,
You actually think
what are you really saying? You know? Like, what are my chances of passing this test? I'm 85% sure you're gonna pass. You're like, oh.
But you can't do
it
a
could be
number.
much worse. You could say I'm 52%.
Oh yeah. I mean, there's always a bigger fish. You know, like so there's possibilities everywhere. But in this interval, what's happening is you're getting away from certainty in terms of the width of the interval, but you don't want to get too far away from certainty in terms of the percentage value. All right. So if I use 90% as a benchmark, I mean, it really just think of the perception. If I were to say, you asked me what are my chances of passing the test, if I give you anything less than 90%, you're going to be a little concerned. All right. But if it starts with a 9, you're probably going to be all right. Oh yeah, I got a 90. Give me another 96, 91, 90.5% chance. You're like, okay, you're feeling pretty good about my chances of passing the test. All right. Anything below that is like, we're not feeling good about this. But as we increase our confidence, we're widening the interval. So what we're looking for is that kind of happy balance where we have the narrowest interval while also having the largest level of confidence. Now, in this case, we're not really looking for any percentage in particular as much as we are looking for the one that's going to best fit this set of values that we have here. All right. So I want an interval that's going to close in as much as possible on this interval, the 720 to 740. So out of the three that I have, 95 fits that. It seems to be the best. Well, actually, I'm sorry, 90 seems to fit that the best. 95 has the highest level of confidence. That happy balance is going to be somewhere in between those two. All right. So if you had to pin down a number, it would probably be in the 90 to 95 range. But I mean, the qualitative answer is really going to be, I don't know. But in terms of quantifying it, that seems to be the most likely possible. All right, and that's what we want to go with. So if you kind of reflect back to this, you have an interval in this problem of 720 to 740, split the difference, you're talking about a margin of error of 10,000. So the individual running this study is saying, okay, I'll take 10,000 more in either direction. All right, so they're allowing for a significant margin for error, but we can always increase our accuracy if we increase the sample size. The problem that we're always going to run into is the practical aspect of statistics and analysis. All right, because yeah, I would love to sample 100,000 people. I would love to have the time to do that, the resources to do that. That's just not going to happen. All right, so what we can do is use our knowledge of normal distributions to help us determine what the optimal n value would be or sample size would be in order to stay within a certain margin for error. All right, so you decide. So this is a little different because you're kind of deciding going in what you want the margin of error to be, and then selecting a sample size that corresponds with that. All right, but it's formulaic in nature. All right, so for one population mean, we have population mean, population proportions. It's a similar approach either way, but since this is the most recent problem that we did, we might as well just kind of revisit it. So Westchester Home example, again, you're analyzing this situation. A brokerage company wants to be 95% confident in your results, and they want the margin of error to be no more than 20,000. So we want to know how large the sample size has to be. Have a high level of confidence. They want to know what the n value would have to be in order to guarantee, or at least, you know, statistically guarantee, which doesn't really mean a whole hell of a lot, but it's as close as we get to proof as possible. All right. So they're saying that the margin of error that we're going to call M is equal to 20,000. The confidence level is 95%, which means the alpha value.
0.025.
Well, it's going to be 0.05, but when you cut it in half, that's where you get the.
Let's just cut it in half now.
All right, so you could run the formula in the way that it's presented in the box here, but the margin of error formula is really just the calculation that we perform after the plus or minus in the confidence interval formula. So it's really nothing new. We're just solving for something different. All right, so that margin of error, the critical z multiplied by sigma over the square root of n, if we just solve that for n, you get that formula in the box. Now, since we have a ready-made formula, we might as well use it, but it's basically saying we never really needed to know this formula to begin with. All right, so n is equal to z sub 0.025 times 60,000, because that's our population standard deviation. The margin for error or margin of error, terms used interchangeably, 20,000, quantity squared. All right, so, well, it's just going to be 3 times our critical z squared. So second vars, inverse norm, popping in the 0.025. You get that number, multiply it by 3, square it, and round it. We want to go no less than 30.573. So we're going to say 35. 34.573. So we're going to go no less than 35. So even if it was 30.273 or 30.073, we'd still round it up because that decimal equivalent is still worth an entire value. So always rounding up when we're looking for sample size. So 35 individuals will get the job done under these circumstances. All right, but you could play around with the critical z value because, you know, if I wanted 99% confidence, then I would go Z sub 0.005, and then see what that corresponds to. You know, you can go 90, 95. You can make up your own if you want. If you really do want to tell somebody that you're 85% confident, then you can do that. You know, it's Z sub 0.075. I don't know how meaningful that is, but it's something that can be done. All right. So that's how you determine the optimal sample size.
So is Z alpha divided by 2? And how do we find, do we just put that in our calculator?
Yeah, that was the inverse norm. All right, so the formula for one population proportion, same ingredients as the margin for error formula for the one population proportion confidence interval. It's just, again, solving for n rather than the margin for error value. All right, things to be cautious about. So, you know, I'm not going to trouble you with taking you through that. I'll give you time to practice that stuff down the line. Just there's no need to take you through another calculation. It's pretty much the same thing. Confidence intervals, you need to have a simple random sample. If you want to use either of these formulas, basically any formula that involves a Z, you need to have a sample size of at least 30. So that's a condition that needs to be accounted for, either in the framework of the problem or you need to make that assumption. In order to use the formula, you need to know the standard deviation of the population. All right, so whether it's something that you calculate using the one population proportion, or if it's something that's flat out given to you in the case of the population mean situation, either way, you have to have access to that information. All right, so those are some things that you're gonna have to focus on down the line, because I'm gonna make a claim, and you'll let me know down the line whether I was right or wrong. I think that the only thing that you're going to struggle with in this unit is the assumptions and stating them, right? Because when it comes to calculations, writing conclusions and things like that, I don't think you're going to have any trouble with that. It's remembering to indicate all the assumptions that need to be in place in order for you to use a particular confidence interval approach or hypothesis test. That's where people tend to stumble, all right? And so you gotta kind of make that a point of emphasis, all right? So put a star on this, highlight it. I don't know, the cautions at the bottom. It's stuff you gotta know, all right? Very, very important. Now, the more realistic situation when it comes to population means is a case where you don't know what the population standard deviation is, because what I was saying yesterday is if you know the population standard deviation, odds are you knew the population mean in order to compute it to begin with. All right? So here we're assuming that we don't know the population standard deviation, and so we're going to work off of what's called the sample standard deviation, but using a different type of distribution. All right, that distribution is known as the student t distribution. We just call it the t distribution because student t distribution sounds stupid. All right, so all of that is kind of stated here, but in this little paragraph at the bottom, I walk you through just where this concept of degrees of freedom come from. Way back in the beginning of the course, we talked about calculating standard deviations, and that there was a difference in the approach between the standard deviation for a population and for a sample. And so this actually justifies or helps to kind of bridge the gap in understanding between the formula for the standard deviation for a population versus that of a sample. All right, so assume you have a sample set with 5 values whose mean is 45. How many values do you have control over? So basically you could select any numbers that you want, but at some point you're going to lose control over the values that you can select to be as part of the data set. We want to know when that happens. All right, so if I'm telling you that my mean is 45 and my n value is equal to 5, then the sum of the values in the set is going to be n times x bar, or 5 times 45. Which is what? Unit circle numbers, it should be easy. 225, yeah.
Oh, yeah.
Yeah, unit circle numbers, not made up numbers. So we can choose any numbers that we want to be part of the set, but if they have, all 5 of the values have to total out to equal 225, we are going to lose control after a certain point over what the numbers can be. All right. So let's say that the first number is 40. Just making it up. That's going to leave me what for the remaining values?
185.
185. All right. So then let's say the next value is 35. Try to make it reasonably clean. So we're down to 150.
And then can we just do 350s?
We could, but you're not really going to do 350s. You're going to do 250s. So let's say we want to do that. I'll go with your idea. You have 50. That's my third value, which brings me down to 100. Then you want another 50. But at this point, I've lost control over what the remaining value can be. I have no control over this. The 5th value is predetermined. All right, so you have control. In a data set, you have control over all but one of the values that make up that data set. All right, so given a mean,
Math, this formula will help so much for math.
all right, so given a mean and a number of values in the set, you can select all but one of those values to be in the set. All right, so your degrees of freedom, df, would be equal to n minus 1, because the last value is determined for you based off of the decisions that you made prior to that. Now, as it turns out, depending on the values that you select, and this should make sense, if you have a mean and a number of values in a data set, you can select any number of different possible values. I mean, for example, I could have selected the first 4 values to each be 1. And then that would make the last value 221, necessarily, all right, in order to average out to the 225. All right, so, I'm sorry, average out to 45, sum up to 225. All right, that's going to have a way different distribution than the values that I selected here, which are all generally centered in the 40 to 50 range. All right, I could have spread it out even more. I could have kept it more tightly organized. I could have made them all 45 if I wanted to. All right, so depending on the values that you select, you're going to have the different shape to your distribution. But it's also going to lead you to differing distributions dependent on the size of the data set to begin with. All right, so there's a lot of subsets here where you can have, like I might have a data set that only includes 5 values, but you might have one that includes 30 values. Each one of those distributions are going to have a different shape, but then within each of those distributions will have different shapes. All right, so there's a lot going on here, which is why the central limit theorem is the great equalizer. It normalizes everything. So if I selected values that are skewed in one direction, by applying the central limit theorem, it normalizes it to be roughly bell-shaped. All right, but as it turns out, if I increase my sample size, my distributions will become closer and closer to a normal distribution. all right, which is why we're allowed to use a sample standard deviation to approximate a population standard deviation, because if the sample size is sufficient enough, then it will be a good approximator. All right, so when you're thinking in terms of like, I mean, just general calculus concepts, the concept of a limit, you generally think in terms of where y is going as x approaches a particular number. Here, it's really saying what is the overall shape of the function moving towards as the sample size increases. All right, so when you're dealing with your symmetric bell-shaped curve, it's going to be short and wide for small values of n, but as you increase the sample size, it gets taller and skinnier until it approximates the shape of a normal distribution. And then you could use a z distribution to approximate all the data points. All right, so that t distribution is going to become a more powerful device for us than the normal distribution, because it's going to apply in many, many more situations, because any situation in which we don't know the population standard deviation, which is going to be most of them, we're going to have to rely on this method. All right. So some similarities and differences between the z distribution and t distribution. Really, it's not structurally very different, but the key difference is under variation. All right, S varies with sample size, but it's greater than 1. Here in the z distribution, z is always, sigma is always equal to 1. All right, that's our benchmark. So let's tackle a problem. And I'll just take you through the whole shabiggity bangity boom here, rather than letting you walk through it on your own. I go back and forth on whether or not I should have these instructions typed out. I think I should leave it, but I don't like rely. I never refer to them. First step is going to be to type this data into your calculator. All right, so let's get that information in. We need the mean and standard deviation. All right. I mean, or not, or you don't have to, I guess. But since the question is telling George specifically to do it, yeah, might as well. Oops. All right, so data's in, double check. The assumptions. We need to make sure it's a simple random sample. Generally, that's going to be stated in the problem. If it isn't, there's no way you can attempt the problem without making it an assumption that it is a simple random sample. As we move further, I'll talk to you about the difference between an assumption and a condition. But generally, if you have it in your mind that a condition is an assumption that is verifiable, then you're going to be in good shape. So basically, if you can test an assumption, then it becomes a condition that can then be verified. All right? If it's not something that can be verified based on the data or the parameters in the problem, then we just have to assume that it's true. So if this problem is written basically exactly the same way, except in the second sentence it says, he takes a sample of 15 John Jay students and gets the following numbers, then the assumption would be that it's a simple random sample, right? We would have to actually indicate that. all right? As opposed to, so just thinking about the test, this isn't just AP, this is the test. You would have to write assumption, simple random sample, right? If it's not written in there. But in this case, it says it flat out in the problem, so you'd write condition, simple random sample, you put a little check mark next to it, and then write stated in problem, all right? So it's little things that you're not gonna really be overly thrilled about having to do, because I think you could demonstrate a great deal of knowledge and understanding without doing any of this stuff. However, these are the requirements for the College Board, all right? So, stat, calc, uno, list one, calculate, we have our mean and standard deviation. All right, so we have that information, so we jot it down somewhere. We're gonna work with the real values anyway. 620 is fine. We do need to test the normality of the data set. So there's two ways to do that. Well, actually, there's a bunch of ways to do it, but two ways that you might consider doing it. One would be to make a normal probability plot. The other would be to graph it and see if it's roughly symmetrical. All right, graph it in the form of a box plot. Okay, so if you take a look at a box plot and it looks like it's roughly symmetrical, then you can be satisfied that it is at least close to normally distributed. If you create the normal probability plot, this calculator won't do that, so I can't. I programmed one of my calculators to do it, but I don't think it was this one. Yeah, definitely not. So either way, most people go with the box plot approach, right? Because if it's symmetrical, then you can make the assumption of normality, all right? And we're also looking for independent events, all right? Now, in this case, I don't know that there's a way that we can make that assumption, or I'm sorry, test that condition, other than to glean it from the problem itself. George is attempting to find out how many text messages the average John Jay student sends in a month, all right? So what are the assumptions of independence? Well, you got to assume that one person sending a text has nothing to do with another person sending a text. Can we always assume that that's true?
Not if they're all in a group chat.
Not if exactly. Like if one person's communicating directly with another in your sample, then that could skew things. But in order for this process to work, we have to assume that they are independent of one another. All right. So in the write-up of this study, George would have to indicate that one of the potential flaws would be if there were basically, working at cross purposes. You have one group that was texting another group skewing the data, all right? So that could be a problem, but that's for the conclusion part of it, not for the analysis part of it, all right? So we want to conduct the 95% confidence interval estimate. Very straightforward, because it's the same formula that we used for the population mean situation where sigma was known, except now we're using a t-distribution. So it's x bar plus or minus t alpha over 2 times, instead of sigma over the square root of n, it's s over the square root of n. So we have our 101.73-ish plus or minus t of sub 0.025. I believe it was 95% confidence, times 45.62-ish over the square root of 15. All right, so the big key ingredient is going to be this guy. Second, vars. Here's an option: instead of inverse norm, we're going to use inverse t.
What do we do for DF?
The degrees of freedom is going to be n minus 1. So n is 15, so we're going to put in 14. Now I have to put mine in differently, but it's going to have the same ingredients, 0.025 with 14 degrees of freedom. And so we get this value, which should be pretty much in the neighborhood of what you would get if you use inverse norm, but different enough that it would change the results. All right, so 101.73-ish plus or minus this number, which I'm going to store in as t. But I'm going to put the value 2.145-ish times 45.62 over the square root of 15. So I'm just doing that for the purpose of writing appropriate work. But in the calculator, I'm going to use all the shortcuts I can think of in order to get this. Like, for example, var's stats, var's option 5, for my x bar. Because it came up, because my t statistic came up as a negative, I'll do the plus. I'm doing t, so alpha t times my fraction, which is my standard deviation. So var statistics, find sx, and divide it by the square root of 15. That's not a 15. That's a 15. So that's one bound of my confidence interval. And then I'm just going to do the same thing, but this time with a minus sign. Before 7. All right, so this would be my confidence interval. And so I would state we are 95% confident that the true population mean, number of text messages, is between these two values. So the only thing I'm going to ask you to do for homework, it's very, very minimal. Do this same thing again, but use the t interval function in your calculator. It should take you like 10 seconds. It's in the stat test menu. All right, it works pretty much the same way as the z interval function. It's a nice nifty shortcut for this, but you're going to need to know how to do it by hand. But it's nice to know what the answer is going to, obviously.